Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next tutorial in the Coding a 2D Game Engine in Java series. So in the last tutorial what we did was we went over scene management and the delta time variable in the game loop. So I would highly suggest you check that out if you haven't. In this tutorial I'm going to be purely explaining there is going to be no coding, but it's super important, especially if you've never done any graphics programming on the actual graphics card. So what is programming on the graphics card? Why is it so hard? What is it like? Well, it's actually a lot different than programming on the CPU using high-level languages. You have to use a lower-level language, and there's a whole pipeline that it goes through. And in order to understand why it's so difficult, we sort of have to take a look at how we send data to the graphics card and how it gets processed. So that's what we're going to do today. We're going to do a high-level overview on the entire stages of the graphics pipeline. This is going to be mostly taken from the OpenGL tutorial Hello Triangle, which I will have a link to in the description. And in case this is not clear enough, I will link some other videos by Thin Matrix because he has some really good explanations on this stuff too. So just in case you want some further material, there will be links in the description that you can check out below. So let's try and see how all this stuff works. Before we take a look at how things are done today, I think it's important to look back on history and see how things were done initially. Now, back in the 80s and 90s, we had this thing called Raster Graphics. You may have heard of this term. It's really simple. All it means is basically that the screens were fixed width and height, and so they stored the amount of pixels in a flat array like this, with the RGB for the first pixel, RGB for the second pixel, so on and so forth, going across the screen, and then they would blit the image, B-L-I-T, which means they would just basically copy this buffer straight to the screen. They didn't have to worry about really stretching it too much because the screen size didn't vary that much. Say, for example, you were creating Mario, they knew they were creating it just for the SNES or some other system. The most they would have to do is just stretch the pixels, which was done by some internal tools, typically done on the operating system. So they would just have a fixed size of pixels that they would blit onto the screen. Raster graphics, pretty simple. Today, however, things are quite different. The reason they're different is because of the move to 3D, first of all, and the move to using graphics cards, which uses this 3D stuff. So the way that 3D works is it goes through a whole pipeline that we have to sort of program a few parts of and send all this data to the GPU. So I have the pipeline here, which is taken pretty much directly from that tutorial too, which you can find more explanation in detail on the website. It is written for C++, not Java. But basically, the reason that we have this whole shape assembly thing and stuff too is because in modern GPUs, you don't send pixels, you send shapes. And so typically these shapes are triangles. So in our case, what we'd want to send is a bunch of squares since we're sending all sprites in 2D stuff to the GPU, right? So we're going to be sending in these lists of vertices. It's a whole different way of thinking. No longer thinking about pixels, you're thinking about vertices. So this would be like V0, V1, V2, V3. And the way that the graphics pipeline works in modern technology is it first goes through a Vertex Shader. This is something we program. The Vertex Shader transforms these pixels, these coordinates into normalized device coordinates. So basically, you have your world coordinates, which is some points in 3D space and stuff, which makes sense to you. And then what you do is you multiply it by some projection, which is basically like the size of the screen that you're on and everything and the dimensions. And then it transforms these coordinates so that they are now in a range that is normalized for the computer. And we'll take a look at more what that means in a second. Next stage, the GPU does this automatically. So we write a shader for this. We have to handwrite this one. Shape assembly is done automatically by the GPU. All it does is you can tell it stuff like GL line, GL triangles, or GL strips. Or I mean points, I'm sorry. So line is actually strip, and then you have GL point. And so these three different flags basically tell the GPU, hey, I'm sending you a bunch of points. This is how I want you to process them. So if you have triangles, it's going to assemble them into triangles. If you have points, it's just going to leave them as points. And then if you have strip, it's going to turn them into like lines. So this is actually strips. Next, what it does is it goes through something called a geometry shader. This is something also programmable that you can do yourself, but most people don't, because there isn't really much use for it unless you have very specific use cases. The only thing I can think of where it kind of makes sense is, say you have some like 3D ocean, and so you know that they move over time and the waves move, and so a geometry shader basically allows you to add geometry, to add more shapes. And so maybe you want it to move like noisily and actually move up and down and create more geometry or something. It's just, there's not a lot of use cases for this. So what you see here is sort of an example of how it could have been used. This point got added and now you have 2 triangles instead of 1. So geometry shader allows you to make more shapes. Next phase, it goes down here to rasterization. So you'll recognize that because of our raster graphics. This is the process of converting these abstract shapes into pixels. And so the GPU does this automatically too. And it basically turns all of the stuff that we have passed it into pixels appropriate for the device that it is drawing to. After that, it goes through the fragment shader. This one is another one that we can program and that we have to program. So the vertex shader and the fragment shader are going to be our primary sources of concern because these are what we have to program. The fragment shader is in charge of coloring every single one of those pixels. So you can define basically a way to color all the different pixels that you now have. And it will pass them to you in sort of weird way. We'll take a look at a couple of these programs so we can explore a little bit more about how they work. But basically what you would do in this shader typically is lighting calculations, any sort of like cartoon shaders or something like that that you have. PBR rendering, all that stuff is done in the fragment shader typically. The last stage is tests and blending. Now we don't have to write this explicitly, but we do have to tell the GPU a little bit about what kind of blending we want and the tests we want. Say you have an object that is in front of another object. This is the part where the object closest to the camera would stay, and then GL would blend between this and the one in the back. So if it was a solid object, then it would just clip the object behind and only show the object closest to the camera. If it was something like glass, then it would blend between the light color. So then, like you had red stained glass, it would make it sort of a reddish tint for the object behind it to give it that glass look and feel. And so that's sort of what the blending is and the test. Also, the clipping happens in the shape assembly stage. So if there's anything lying outside of the screen, they get clipped from this whole thing. So because now you have them in normalized device coordinates, so you can tell what is inside and what is outside, just so you know. Now I talked about normal device coordinates and vertex shaders. What normal device coordinates are is it's basically just defining the screen from -1 to +1. -1 is left side screen, +1 is right, -1 is bottom of the screen, and +1 is the top. So normal device coordinates. It's basically just so that it's easier for the graphics card to make all these calculations and stuff since they are in that normal range. Now, vertex shaders expect, remember we said that we have to think about things in terms of vertices. They expect an array full of vertices. And so what I have here is something called a VBO, or a vertex buffer object. This is something that we define, and it's basically our collection of vertices. Now, vertices can have many things attached to them. They can have colors, they can have texture coordinates, and all sorts of stuff. So this could be a red pixel, this could be a green pixel, this could be a blue pixel, and this one could be a black pixel. And basically what the GPU expects is, okay, if we want to send all this data with our pixels, then we have to encode it into the array directly. And so basically what our VBO will look like is we'll have our position in the X coordinate, our Y position in the coordinate, and Z position of the vertex. And typically you will have a bunch of attributes that you define yourself. So I have RGB and TX, TY for texture coordinate X and texture coordinate Y. You do not need these. These could be defined as anything you want. So I actually have some shaders where I use some very specific attributes that I define myself. That's what each of these are called. This is a position attribute is what we could call it. This is called a color attribute, and this is called texture attribute. And now we also have to define to the GPU a couple of these terms. We have to define the offsets of each attribute. So we would say, oh, our R color, that's 3 offset from the beginning of the vertex. And then we have to identify the stride, which basically tells the GPU, this is how long you have to go between each vertex. And so the stride would be 8 since there's 8 things in there. And I believe this is in bytes. So if you had like floats, then you have to do 8 times 4, and we'll explain more of that once we go into the code. But that way, basically, so the GPU knows, oh, if I'm here, if I want to get the next attribute, I have to go 8 out, and then it knows it has to go somewhere out here, and it can calculate between each attribute and between each position, everything. Now, there are a few other things that we have to send to the GPU. If you think about each of our sprites as a single square, then how do we group these squares together in a way that makes sense to the GPU? How do we make sure that each of these is like one object, right? So this is one picture on our screen. We want this to be one object. Well, the GPU has these things called VAOs, which are vertex array objects. And so basically these define sort of the attributes and the vertices. So this contains all the information about, okay, this is the VBO I'm using first of all. Then it tells you, hey, okay, this is where attribute 0 is. So this is where the position is, and then you sort of tell it, hey, the stride is this, the offset is this. Then you say, hey, this is where my attribute 1 is, and the stride is this, the offset is this. And the VAO will contain all that information. Now, another thing you have to consider, what if you want to draw these two triangles? Well, you could do it two ways. You could go, here's the first vertice, here's the second vertice, here's the third vertice, that's the first triangle. Here's the fourth vertice, here's the fifth vertice, here's the sixth vertice, that's the second triangle. Now you'll notice we just duplicated two of those vertices, which is really inefficient in memory and wastes time in general. What you would like to say is, here's vertices 0, 1, 2, and 3. I would like you to draw a triangle from 0, 1 to 2, and from 0 to 3 to 1. And the GPU lets you do that. So you just have to specify one more buffer object. This is called an element buffer object, or EBO. And basically what it allows you to do is to define these coordinates, or these indices, which define which vertices you're using. So you can go, hey, I want to use 0, 1, and 2. Then the GPU would go, okay, let's look into our VBO. Here's vertice 0. Here's vertice 1. And then, oh, here's vertice 2. And so then it would use this, this, and this. Then it says 0, 3, 1, and so V3 would be somewhere out here. And it would be like, okay, I'll use this vertice, and this vertice. And it allows it to index directly into the array and figure out which attributes you want to use. This is really helpful because then, like I said, you're not duplicating these vertices anymore. You're just saying, just use the ones I already have because we don't need to duplicate those. Then you can create as many VAOs as you want. So say you wanted another square, you could create another VAO. Now this is actually quite inefficient, and we will do a smarter way than this, because if you create more VAOs, that creates more draw calls, which ends up lagging your game a lot more. So we'll figure out ways to group it so that we can have two squares in one VAO, which I hope you can begin to see how you might do that. And then we can just have one draw call, which speeds up our game tremendously. So we'll look into that in a future tutorial called batching. Now we have to take a look at the thing called Fragment Shaders. So what are Fragment Shaders exactly? Well, they sort of define the way that the pixels look on the screen, right? They define the colors. So basically, say you had a square on your screen right here. If we zoomed way in and took a look at each individual pixel, you can sort of think of the fragment shader like a big parallel processed program. And basically you have a program running for this pixel, for this pixel, for this pixel, for this pixel. You have a program running for every single one of these pixels at the same time. And that's essentially what the chipset does. That's why it's so much faster, because instead of having to go and loop through every single pixel, you can do a whole bunch of pixels at the once, because that's what the GPU is made for. And so you basically have a program running for every single pixel, and you have to think about it in terms of not, okay, I want a color red here, green here, blue here. It basically changes and it interpolates. So if you have a red pixel here and you want a green pixel here, what it's going to do is it's going to interpolate between these two and give you a gradient from red to green throughout here and basically use those colors. And it does this automatically. It's very confusing. This is one of the hardest parts of shader programming that I think is to grasp is fragment shaders, because trying to think about this in this way is completely different. There's a great website called Shaderbook. I think it's Shaderbook. I'll have a link to it in the description. And it's really great if you want to learn more about shaders and how they work and stuff. It uses a slightly different language than we'll be using, but that's fine because the concepts are really what the hardest part of this is. In the last phase, we have to do manually. So as I said before, there's a lot that goes into this. So we've basically defined to the GPU, hey, we have this vertex shader, we have this fragment shader. Hey, GPU, we have this VBO, this VAO, this EBO. We want to send all this data to you, and we want you to draw it. And so then the GPU is like, okay, cool, but how do we tell the GPU which vertex shader and which fragment shader to use and all that stuff? Well, we have to do this thing called compilation and linking. And if you don't know what compilation is, it's basically taking a high-level language like Java. So you have some Java syntax, if true, blah, 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 do, well, actually that'd be a bracket, do, blah, 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 which the computer cannot understand. And Java actually compiles it to some bytecode where it would be like JMP if false to register 32 or something like that. And then this actually gets compiled again to machine code, which is just a bunch of zeros and ones. And then the computer can run this. And so compilation is basically taking something that looks like this and taking it all the way down to that machine code where we can understand it. So we have to do this manually for our shaders. And so we have our vertex shader, which is a program we wrote. We have our fragment shader, which is also a program we wrote. What we have to do is we have to tell OpenGL, hey, compile this and compile this. Then we take our compiled output and we say, hey, okay, these two shaders are linked together. We need you to link this executable code that we have generated for the GPU and this executable code that we have generated for the GPU. This is our fragment, this is our, this is our fragment, this is our vertex. Link them together so that they know how to find each other. And we have to do all that manually. And then and only then we can use these shaders, and we can use them in conjunction with a VAO. So you can actually use one shader for any amount of objects, any amount of VAOs, and then you can use a different shader for those same VAOs. So the cool thing about this is you can change the entire look and feel of your game by just changing the shader. And that will change every single object in your game because the VAOs are basically just our objects in memory. They're just our squares, our sprites. And so you can just use any shaders you want with these sprites, and it doesn't matter to the GPU. It will do the same steps on them no matter what they are. So high level overview. I want to take one more look at just a shader real quick so we can sort of look at them and see how they work. So let's take a look at a fragment shader and a vertex shader and see some of the concrete stuff that they might do. What I have on here is a couple of shader programs. So you can see the top one is a hashtag type vertex program, and they're in the same file. And then the bottom one is hashtag type fragment shader. So this is our fragment program, and this is our vertex shader program. And so basically what these are sort of definitions to the GPU of how we want to do these things that we talked about in that little bit about how these things work. So remember I said for the vertex shader, we have these things called VBOs, right? And they have these attributes that we attach them, 0, 1, 2, 3. Now each of these attributes points to some position in that array. So basically what we're saying here is we're getting some array that we already defined where the position is defined as the 0th attribute, the color is the first attribute, the texture coordinates, second attribute, and the texture ID is the third attribute. And so those would be defined just sort of as that whole stride offset thingy. We'd be like, oh, offset of 0, offset of 3, or whatever we have to do, offset of whatever this one is, and oh, the stride is however big each of these vertices are. And so we get all those passed in as these variables. Then we also define some variables that we're sending out to our fragment shader. So typically, the shaders go vertex to fragment, and you can send data between them. So you can say, okay, I want to send this data to my fragment shader, which is why we have to link them together. Then we have these things called uniforms, and these are a little bit different. They're like global uploads. So basically, you can say upload a variable and just upload it to whatever shader is currently being used. And we'll talk more about these once we actually get into uniforms and shaders specifically. Now we have our main function, which is what is automatically called from the GPU. And basically it expects a GL position to be returned. Notice GL position is not defined anywhere up here, but it's just automatically inferred to be returned by our shader. So we use some of those variables that we had up there and sent the out variables to some of the variables we got in. And then we basically transform from world coordinates to normalized device coordinates right here with this multiplication. This is actually matrix multiplication. So it works a little bit different than normal multiplication, and it works with linear algebra. I can do a primer on that if we really need it. But basically all it's doing is saying, hey, the out position is going to be normalized device coordinates from our world coordinates, which were passed in up here in this A pose. Then it all gets passed into the fragment shader. And so the fragment shader is that big parallel processed unit that operates on every single pixel. And so basically we have some more of those uniforms, and then we have some of those variables that we got passed in from the out variables here. And so they're the same name, and that's sort of how GL translates them and finds them and everything. And basically I've made this one pretty simple for the first fragment shader. It's just a texture sampler. And so all it's doing is it's sampling the texture. Right now it's not actually sampling it from anywhere good. We're just setting the color here. And then what you would do is you would say, oh, text color equals texture sample. And then you would pass it in the f text chords dot x. Actually, you could just pass it in the f text chords. And so basically what this does is it sets it to the texture of whichever pixel we're on. So say we had a 32 by 32 pixel. What this would do, because remember, these are passed in the variables sort of interpolated. So if we were in the middle of that picture, what it would do is it would have an interpolated value, not the actual value that we're expecting. And it would sort of pick a pixel in the middle of that picture, and then set the color to whatever the color of that picture was on our actual screen. It's confusing. It's really complicated. Like I said, there's going to be additional resources to sort of understand this stuff a little bit further. And once we actually start coding these and seeing how they work, hopefully you'll begin to see how they work a little bit better. But check the description for more resources if you want that. And we're going to try and code all of these concepts tomorrow by drawing a triangle to the screen. Actually, probably a square. Drawing a square to the screen. Using every single one of these concepts to see how it all works in action. And that's going to be quite a big task, but we'll get it done. So if you guys like this, please hit like and subscribe. And if you need any additional help, just leave a comment below and I will try and reply to that as succinctly as possible with some good information. So hope you guys like this. I'll see you next time.